Okay, so welcome to the 24th lecture, and this lecture is going to be a sweet little introduction to complete metric spaces. And the definition of a complete metric space is every Cauchy sequence converges. Okay, so if you don't know the Cauchy sequence, you should, it's basically any sequence xn, and for any epsilon that exists at n such that for any, it gets arbitrary close. Okay, it gets arbitrary close. Okay, for any zone that exists such that it gets arbitrary close. Okay, so a metric space is complete if every Cauchy sequence converges. So here's some remarks. If a metric space is complete, then any closed subset is also complete under the restricted metric. And to verify this, so suppose you have a Cauchy sequence in this, which implies is a Cauchy sequence is that, and this is complete, so it converges. But A is closed, so the limit must be an A, which shows that this is complete. And secondly, consider the bounded metric, standard bounded metric. Then xd is complete if only if xd bar is complete. Okay, so sometimes we just need to show this is true, it is more convenient sometimes. And also, if every Cauchy sequence has a converging subsequence, then the space is complete. And this argument just follows by triangle inequality, and I suggest you to verify this by yourself, okay? So here's a theorem that the Euclidean space is complete under both Euclidean or square metric, okay, for any finite. So this is what I mean for a Euclidean spaces. So first we have this inequality holds, okay? Thus we just only need to show that under the square metric is complete, right? So if this is complete, then it follows by this, right? It follows by this is like, this is also complete. Okay, so we just need to show this. To show this, well, for any Cauchy sequence in this, we see that Cauchy sequence is a bounded set in an RK row, right? Because first we pick n such as a cutoff for them to be arbitrarily close. We just pick epsilon equal to 1, and if we just let m be the maximum of from x1, the distance from x1 is 0, until the distance from x minus 1 to 0, all until the xn 0 plus 1. And from here, it's just by triangle inequality, we see that this is true. Okay, so every sequence, every elements in the sequence, their distance from 0 must be bounded by this big M. Okay, thus from here we just see that this sequence, this set, lies into a compact set. Okay, and a compact set is sequentially compact. So by the remark, right, sequentially compact, which means that it has a converging subsequence. So every sequence has a converging subsequence, right? Sequentially compact means every sequence has a converging subsequence. So we're done. To deal with the finite product, we're done with the finite product, right? To deal with the countable product, R omega, first we need a lemma. Is that let X be a product space in product topology and X in a sequence in X, then Xn converges to X if only if each component converges to the component of X for each alpha. Okay, this is in general for any product space. And first of all, this direction, because the projection map is continuous, so it preserves convergence. So this is done, right? Because the projection map is continuous. And for the converse, so we just pick any basis that contains X. So for each finally many U alpha that is not equal to the entire space, we can argue our convergence here, right? We can just pass down to our convergence. So X pi alpha xn converges pi alpha x. We can pick a cutoff such that, right, every single one of those lies in the neighborhood of this, right? Now, since there are finally many of them, so we can pick the maximum, right? So from now on, we have this relation is true for any alpha, which precisely means this is true, right? So we have, for any basis contains x, we have an n such that for any n greater than n, we have xn is in the basis, which shows that Sn converges to x. Alright, so we're done. Now with this lemma, we can just prove that R omega is complete. And the metric is defined as this. Okay, so this metric, in my separate video on metrization of R omega, I use this metric to show that this metric on R omega induces the product topology. Okay? So R omega, it is also complete for some metric. And to show this, we just use the lemma. First of all, for any Cauchy sequence and R omega d, since we have this is true by definition, okay? We have this is true for any x and y. Okay, so this follows from the definition, right? Definition of dxy. We just move I, we just move I over there. Okay, so from here, for each I fixed, because this is Cauchy, right? It is Cauchy under D, and for I fixed, it won't change anything, right? It won't change anything, which pass down to that each of pi I of xn is Cauchy, right? So if each component is Cauchy, and because this is complete, so it converges a sequence, the sequence converges to a real number, then if each component converges by the lemma, the entire thing converges. Okay? So R omega is also complete. So here's an example for incomplete spaces, like 0, 1, and for the sequence of this. Right, this converges to 0, but 0 is not in the space. Okay, so it's just some, just to let you know that not all metric spaces are complete. What about arbitrary products of R? Well, from here we need to define a metric that is called a uniform metric. So first of all, let's just start with a metric space and a bounded metric. For any f and g, a mapping from j to y, so i.e. there are elements from this, we can just define their uniform metric as the supremum of d bar of all f alpha g alpha. And this is defined because it is bounded by 1, right? So this supremum definitely makes sense. And this is a metric. You have to, it's easy to verify this is a metric just by triangle inequality. From triangle inequality of this gives the triangle equality of this. You can just verify this with the definition of supremum. And this is a metric which is called a uniform metric corresponding to D. Corresponding to D. Because we have D, D gives our D bar, and D bar gives our rho bar. Okay? So this is rho bar is a metric or uniform metric corresponding to D. Now, what about, for this metric, you can see immediately that if it converges on the rho bar and it converges uniformly under D, right, or D bar, same thing. So here we have a theorem that if yd is complete, then yj rho bar is complete. Okay, if this is complete, then yj rho bar is complete. First of all, this is complete implies that we have d bar is complete, as I said at the beginning, right? So we just let any Cauchy sequence inside this, and for any alpha and j, we have this is true because it's supremum. Thus, each of them, right? Each of them is a Cauchy, is Cauchy y d bar, so it converges. So for each alpha, we have a y alpha. Now let's just suppose there's a mapping that takes each alpha to y alpha for each alpha, right? We may just guess that this fn converges to f. Well, this is just by some analysis tricks. So for any epsilon greater than 0, first we pick an end cutoff of them being Cauchy. Thus, from here we just have this is true for any alpha and j, right? Now, what we're gonna do is that we let m goes to infinity, so that it goes to f of alpha. Okay, so fix n and alpha be fixed, we can let m goes large. What we have is that this is less than equal to epsilon over 2. And you might guess why, right? You might guess why. So to show this, just consider the sequence am defined as this m gives this m, and n and alpha are fixed. Okay, they are fixed. And am is fm. Okay, first of all, since fm converges to f of alpha, right? So am converges to fn of f of alpha. From this is by triangle inequality. Okay, you have to verify this by yourself. It's just by a single triangle inequality gives this. Now, so we have am converges to this, but all the am, right? We have this is true, right? Which means that all the am are inside the open interval with, 0 with radius epsilon over 2, right? Right, yes. So, which means that from here, right, this d bar, is a metric on R. Sorry. Oh, wait a second. Okay, maybe this is not too, this, oh, I thought I'm doing with, wait. Oh yeah. It is a real number. Oh my god, I'm tripping. Okay, a metric gives you a real number. So this is a sequence. This is a sequence in real number, right? Sequence of real numbers, and it is inside this, and it converges, right? So the limit must be inside the closure, and the closure of this is just this, right? So this is where I have this. This is true, right? Because the limit must lie in the closure of this, and the closure of this is precisely equal to this. Okay? And yeah, from here, for each n and each alpha, right? Which means that for any alpha, we have this is true. Well, which means that this is true, right? If n is like so we're done, right? Yd is complete, then yj row bar is complete. Now, to specialize, if we just consider J, we replace J with X, where X is a topological space. Then we can just consider the special subsets, special subcollections of all the continuous function and all the bounded functions, right? All the bounded functions, where Y is still a metric space, okay? So here we have that if this is complete, then the continuous function and the bounded functions, they're all complete on their row bar. First, we already have yj row bar, yx. We already have yx row bar is complete, right? So by the remark, if we can show that they are closed in this, then we're done, right? So we just need to show that they're closed. To show that they're closed, we just need to show that it contains its limit points. So suppose f is a limit point for a continuous function, then the existing sequence converges f on the row bar. But converges on the row bar really just implies it converges under d bar uniformly. And by uniform convergence, we see that if this sequence of continuous function converges to uniformly to a function, then this function must also be continuous. And for bounded functions, if f is a limit point of a bounded functions, again, we have a sequence converges to it, which means that we can just pick n large enough such that this distance is less than 1 over 2, right? So from here, we pass down to every x, we have, because they're less than 1 over 2, which is less than 1, right? So d and d bar are the same. And so the d of them is less than 1 over 2, which means that the diameter of fx is like equal to the diameter of this plus 1, of fnx plus 1. Okay, and this is again by triangle inequality. Everything is triangle inequality. Okay, and which shows that f is bounded. So we're done. Okay, so this is a sweet little introduction to complete metric spaces, and I'll see you guys next time.